Okay, hello. This is video recording for the sets of linear combinations and their images, how it geometrically represents plotting the vectors into the graph right here. And we can go ahead and interpret those those numbers as to see how this would work. So starting off, we set everything to 0. The variables, the a, b, and c vectors. Then we will start doing for a, we will put 4 with the R1. So we would set this one to 4, and this one would be 1. Oh, sorry. And then R1, then we set it up to 2, 5, and we will describe how these scalars will relate to multiplying it by the a. So as we do 1, so this would be our vector a, which is the blue one right here. And if we multiply it by 1, then it's just 1, that vector right there. So if we were to move it to 2, we can see that this would be by 2. So it would end up by the second one right here, the second dot, the green dot. And also, once we put it up to 5, we can see that the dots expand even farther. So this would go up to 1, 2, 3, 4, and 5. So we can see that once this scalar of 5 is multiplied by 4, we would end up to the 20. And then next thing is that to point A, it would be by multiplying by a -1. So it will mean that this will reverse the way that the arrow is pointing, that a vector is pointing. So instead of going 1 to the right, we would go 1 to the left. So this would equal to -a vector. So it would be up to what, -4. We also have to see minus of 2a. So if we do go back to, sorry, so this would be like the representation for negative. And then 2a would be multiply negative, instead of going twice to the front and ending up at 8, we would end up at -8. Next is the -4a. So it would be went up to 4, and this means it would be multiplied by 4 times in the negative direction, or by the negative. So it would be up to 16. So it would be this point right here. Next is to enter for B. It would be 7, and then we will see the representation for that one. So let's set this one to 0, 0, and then B would be 7. Correct. Yes, 0, 7, 0. And then multiplying this vector by a scalar of 1, we can see that our vector right here is going in the y direction. The other vector was going in the x direction. So we can see that this one will multiply by 1. So we can see that it goes in the positive direction. Our positive is going towards the back. So we can see that our 1 is over here. Once we multiply by 2, we can see that it would go 1, 2, so it would end up at 14. And once we do times 5, we can see that we don't have enough space right here. But what it means is that it would go up to 7, that is the value of the vector, multiplied by 5 would be up to 35 in the positive y direction. So going over here, we would see that if we go back to A and plug it in for 4, you can see that we have 4 right here, our A vector, and our B vector is in blue for the A vector, and then over here in purple it's for the B vector. And we can point out that A plus B. So A plus B would mean that we would go 4 in the positive direction of X and then 7 in the positive direction for the V vector. So at the end, this would end up around here. So it would be 4 to the right and 7 up. So 4 to the right and 7 up, we would end up around here. This will be making our plane and going in the X and Y direction. If we were to do negative A plus B, so this was, sorry, you can see that 1 and times 1. Oh, sorry, it would end up right here for our, in this green dot, are the summation of these two vectors. So if we were to do negative A, we would go 1 to the negative direction, so negative 4 in the negative direction, and then 7 up. So that would be negative 4 and 7. We also 2A plus 2B. So we would set the multiplier to 2 for the B vector. So it would be 1 of A to the right, which is adding, and then 2 for B vector. So we would end up in this dot right here, which would be the summation of these two. And its component, it's how it would look, it would be from the origin up to here. So that would be the summation of these two vectors. Next is part 3. It would be entering for C, 8, 7, and 0. So C would be 8, 7, 0. So our C vector is the blue one, the lighter blue right here. And we can see that describe and point to C. Okay, so I identify the two vectors A and B, where CA and B geometrically point so we would mean that A plus B would give us C. So for that, our A would be 8 and our B would be 7. So these two, as you can see, when we add them, so A plus B, we would end up with C right here, which is the summation of these two equal to this one. So 2A plus B, this would mean the, sorry. So multiplying scalar by 2 for A plus B would mean that it would go 1, 2, and then plus B, which would be 16 and 7. So our C vector would end up right here. It would look something like, oh, right here, 16. So it would be 16 and our 7 right here. That's how it would look for our C vector. Okay, so it will have to be, sorry, 8, give it an 8 and 7. So 2a, this would have to be 4 and 7, which is 2 times a, like that, correct. So now looking at negative a, so it would be 1 negative a and plus b. That way we end up with c. This would be negative a plus b. We would end up around here for c. So instead of going in the positive direction, our c vector would end up going to this direction. Okay. So now we enter c 8, 7, and 9. And so this would be let's turn out the scalars for c. Oh, sorry. 7 and 9, and so we can change r for c. We would do this 4 times 1. That way we can see c ends up right here. And two vectors, c plus a, where they point on screen. So we can say that either this one to be 9 also. We can see that to take a better look, we can go ahead and move this around a little bit more. So we can see that we're using the c direction now, which is c3, b3, and a3. Okay, we can see that have a greater plane and that it's a bit slanted. So we can see that our b vector plus our a vector would end up with our c vector. So we can see that it would go 8 and then plus 7 and 9 going in the c direction. Okay, so two vectors where c2a plus b would point to c. 2a plus b would point to c. So 2a would be, we would have to set a to 4, and then it's scalar 2, which is 2 times a, plus b would end up in that one. So we can see that a is this one, 4 times 2 would be, we would end up at 8, and then plus 7 and plus 9. So this would be the resultant for C. So you can see right here, 2, 7, 2 times 4 would be 8. 8 plus 7, and 9 going in the C direction. So point value -4, 7, 0. I can't set it to -4, but with the scalars, which is 1, it also shows us like here now. So we can see that -4, 7, and 0. This one would be 0. 0, 0. So this is our C value. So we have -4 would be in this direction, and 7 in the positive direction. So our vector would end up somewhere over here. Since it's just doing the scalar vector right here, it's just doing it in the negative. So it's reversing our vector. So yeah, instead of going this way, it should go this way. B minus A would point to them on the screen. So B will be positive, which is 7. We would end up with 7 right here. And then RA would have to be -4. So we can put 4. So instead of going this way, should go this way. That way the summation of the two would be in this direction. As I was showing right now, instead of this was our C, but since it was for -4, it would be going over here, where I'm pointing. Oh, sorry, 14. 14 and 10. So as you can see, our C vector is this one right here. It's slanted going in the C direction, because we have X, Y, and then going in the C. Right. To take a better look, I'll set these ones to 0. Otherwise, you can see is this one right here. Okay. So -A plus 3B. So once we put for -A would be 8 times a negative scalar, which instead of going 8 in this direction, it would go 8 to this one, so over here. And our sorry. This was supposed to. There was. I'm sorry, got a little bit lost right there. Okay, so we got that one. -8, 6, and 15. So for this one, our values, you can observe vectors. So we have C, negative A plus 3B. So negative A would be 8 in the negative direction. 3 times B would end up to 6. So 3 times 2 is equals to 6. And we'll set the scalar to 3. So you can see, we can see the dots right here. So you can see that it would be negative, so over here. And then this is 2 times 3, 2, 4, 6. And this one, we have to set it to 5 to be multiplied by 3. Now it's 15. So we have negative A times 1, 2, 3, 6, and then 15 up. It would end up with 2, 3 right here. Our vector would be up to this point over here. And then we have 2, 14, and 10. Okay, this is our C vector. We go back to 1. C vector right here. And we have A plus 2B, 2 point at C. A would be equal to 2. And this one would be 2B. So this would have to be 7. This one will remain at 5. So we can see that over here. We have 2 and 2B. It's 1, 2. We would end up over C. 1, 2. Oh, sorry. 2. 2, 1, 2. So A would be just 1. So this is 2 right here. And then for our B, 2, 1, and 2. Sorry, 14. 2 will be 1 right here, 2, and then plus A. So it would be end up the C vector. So we have, for C, we have 5, 7, 0. Summation would be A, 5, this one 7, this one 0. Okay, so we can see right here that 5 plus 7 is the same as C. So the equation for the vectors is true, since we have 5 units going this way, 7 this way, and we end up with the same C vector. Next up is 5, 7, 5 and 7, and the vector equation with scalars, B is 3. So for B, is this one, 1, 2, and 3. We would end up with like 21 over here. And then plus 5, which is the A vector, we will end up with the vector that's going over here. So C A plus 3B is not true, since we wouldn't end up with 7 for the y direction. So 5, 7, and the scalars. Yes. So the scalars x and y, where c is equal to x times a and y times b, this can be the scalars for it, since our a vector is in the x axis and our b vector is in the y axis. Next up is for c, 5, 7, 0. We have a 5, 0, 7. The scalars x, y, and z where it's equal to 0. Yes, this can also be equal to 0 doing, oh, I'm sorry. No, it's not able to be equal to 0 because you don't have any other number that multiplied by b would result in a 0 vector for a, and nothing in a that you can multiply to get reduce it to 7 unless you do x, y, and z equal to 0. So the scalar is equal to 0. That would be the only way. So all scalars equal to 0. Then this way you wouldn't end up with, and you would end up just at 0. That would be the only solution. If you have any other numbers aside from 0, you wouldn't be able to subtract them, add them. You would end up with another vector. Scalars. Oh, I'm sorry. Yes, so you can, yeah, you could end up with the scalars. I finally saw it. You can end up with C1, and y can be negative, and c can be negative. So we will subtract these two minus this one, end up with 0. Correct. They are scalars. For C, where, yes, so these two are pretty much the same. And we're almost done with this. Vectors are pointing to relevant parts on the screen. U is equal to 2a. So we have to U is right here. Find two vectors, a plus b. Okay, so we have to find a vector that's so I believe this would be up to 20. So our predetermined vector for u is 3a plus 2b. I'm sorry, but so you could end up with u is equal to 2a plus b. Um, but our predetermined vector is equal to 0. It's just 0. Where v 3a plus 2b. So this is 15 and 10. So we came up with 15 and 10. We would be equal to 10. 2a would be equal to 7.5. So for b is 2a minus b plus c for the predetermined vector. Will be the same thing. So 2a can be any number plus b. So 2a 10 minus 5 is 5. And over here we have, yeah, so b could be either 0 or it can be like 1. And no, yeah, it would have to be 0. I'm sorry. Kind of hard to see these questions. Let's get for the next one. So for C, 3, 5, and 11. So this is our C vector. Two vectors A and B where C are 1 times A and are 2 times B. We can just multiply by 1. 5, this one, this can be 1 and 1. Or this could be also 1.5 times a scalar of 2, or this one times 2.5 and 6.5. That way when you multiply by 2, you would end up with the same vector. So for C, our R1 and R2 would have to be negative. And that's that way when we add them, C would be the negative of C, and we would end up with 0. So we can see that this one would be negative, and then our B value would be this one. So that way these two vectors would cancel out the C vector. 2, 16, 15. So this one would be scalars. So a scalar for this one would be 2 for A, and for B would be 1. That way they add up to 2, 16, and 15. As you can see, once we multiply this one by 2, sorry, 2, we can see that this one got out. So we can see this is our answer. Once it's multiplied 2, 1 times 1 for the v vector. And to be equal to 0 would be this one -2 and this one times a negative. That way it would end up with -2 and with this one over here. It would cancel out the c vector. And 0, 8, 20. Zero, 4, 0. This one back to 1. And 2, 8, 3. Oh, sorry, 5. For it to be equal to 0, we will have to do this one. Oh, we already did this one. 0, 8, 20, 4, 0, 2, 8, 3. So for this one, scalars say yb equal to c. So this one would not end up in the correct c value, since even multiplying by 2 over here, just increase this one, and 2, 2. As we can see, our values for C, for A and B, even if we multiply by other scalars or anything like that, it would never end up with our C. As you can see, this gap right here shows us, and then this would be all the scalars for A and B. So there would be no solution for this one. We wouldn't be able to find that exact value. And 20. So once adding in these two, we wouldn't end up with this one. We would have to end up with a different number. So for A and for B, this one would be multiplied by, I don't know, 6 point something for it to be equal to 20. And A would be times 1, and then B wouldn't be able to be multiplied. Would never give you 0. So this one would be the same, that since we have a 2 right here, we would only have to multiply this one by 0, but nothing in the c direction for this one would be able to be equal to 0, 0, 0. So for linear algebra, we can see that how the components can be seen in the vectors, how they play a big role. You can see how they're manipulated in the space, and how adding each vector would end up with different results, different additions, and looking more of like the space and how everything's moved. And this is my conclusion for the video 1 for our linear combinations. Thank you.